We have like this somewhat provocative title here. I only added a question mark to the title of a paper. And this title pairs a little bit with another provocative title I had used a little bit less than a year ago when I gave this other seminar here, the Software Institute series. What does it mean to learn? And now I won't be giving the same talk again, but I think it's useful to refresh a couple of slides from that talk. I was kind of trying to distinguish several different kinds of learning. One of them being like maybe the simplest, like something like memorization. We learn something in a given context, context A, and then we can test in the same context whether we do still know the same thing. And that's somewhat known as learning. It's like learning a foreign word in a specific language. But what teachers really hope for is that you learn something in a given context, and then in a slightly different context, say B, then you exhibit the same kind of knowledge, or you adapt slightly what you have learned. And this is what in education is known as transfer. And that was the subject of this other talk. And I'm not going to do the experiment again, but just as a refresher for many of you, we had like this very simple geometry task, like what is a right triangle? And here is like how right triangles are always depicted when we're teaching. And then these are like two other conditions that we can use when testing people whether they understand what a right triangle is. Now here there is no trick. I'm not slightly having triangles with angles that are almost 90 degrees. So here is our teaching context, context A, and then we have assessment contexts A, B, C. And there is like this very old study that looked at primary school students and also pre-service and in-service teachers for primary schools. And they showed that, well, almost everybody gets it right for the first case, and the percentages slightly decline for the second and the third case. And unsurprisingly, teachers do well in the first case, but not perfectly also in the second and the third case. So this was all in the past. And then I was wrapping up with this slide that is untouched from that talk that was titled Illusion of Learning. And the two cases here, well, okay, we're learning in context A, and then we're testing in context A, and then it's very easy to get something nice out of it. And this is known like teaching to the test. And also I had this part here in like AI, ML, where it's very easy to have a similar or the same context when you're testing, and then you get like this very nice results, but because of overfitting. So the title of this slide is unchanged from a year ago, Illusion of Learning. And so when this paper came out a couple of months ago with this very evocative title, The Illusion of Thinking, of course, got me quite interested. And so here is the paper for today's talk. Now, before we dive in, a bunch of disclaimers. I'm not like an expert in the subject, so I'm kind of referring to what is there in the paper. I also didn't conduct personally the experiment, so I'm just referring data that is there in the paper. Second disclaimer, this paper has been getting quite a lot of attention because of that word there under the authors. And then it's like, oh, well, this is like Apple's big take on what thinking is and stuff like that. I don't think that's particularly interesting and valid as an argument. I mean, let's try to understand scientifically what is there and whether there are criticisms. And indeed, people immediately jumped on criticism, and then academics, being academics, they produce like this fancy paper, The Illusion of Learning, which is kind of funny. And it's also funny that the first author is credited to be this C. Opus, which I guess is this Claude Opus. Now, this was actually withdrawn then from arXiv and published as a revised version with just the first author, because it's not acceptable to have an AI model as an author, but yeah, whatever. Which like brings up some of the criticism. So the scientific debate around this paper is quite ongoing. But let's see what's in there. And to understand what's in that paper, we need to take a little bit of a step back and understand how to use language models. And I don't need to give you all an introduction to language models, but specifically how to use language models to solve tasks. Now we have like this generalists, language models, and then there are, to my understanding, essentially two ways that are not like entirely orthogonal. One can also mix them, but really two ways to deal with them. Well, once we have like this generalist language model, then we can train the model a little bit more on some task-specific data set, and this is normally called fine-tuning. And then as a user, you can ask this fine-tuned model to solve your new instance of the task, and you may get some answer. Or a different way is, well, let's just take this generalist language model. We can give it some examples that are normally known as shots in the literature, just as part of our prompt, and then we ask the generalist model to solve an instance of the task. And which one is kind of winning in terms of approaches? Well, there was like this kind of fancy paper, 2020, language models are few shot learners, that essentially says, well, what makes sense is just scale up language models quite a while, and this is gonna improve greatly task-agnostic few-shot performance. So we trained GPT-3 that with the 3.5 became the base for ChatGPT. That is the thing that broke the web. Billions of parameters, and then this is going to give you strong performance on many data sets, many tasks. And so, well, it seems that it's just convenient to take a generalist model, scale it up, and then give examples, a bunch of examples of what you want to do in the prompt. And here is an example, indeed, of doing this. So we give an example to the model as part of the prompt. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? The answer is 11. This is all part of the prompt. So some kind of problem. There is some quantity at the beginning, some arithmetic operations, and then the question is, what is the quantity at the end? And then at the end of the prompt, you ask your new problem, your new instance of the task that you want to solve. So here we have like the cafeteria, 23 apples. Then there is I don't know, they used 20 to make lunch. They bought 6 more. How many are left at the end? And this is useful enough to solve many, or like these big models are able to solve many of these tasks with this kind of couple of examples. But this is also not always working. There are still some cases where the model gets it wrong. And so what do we do about this? Well, we could say, well, let's go back to fine-tuning. Or this other paper, 2022, also pretty important, that introduced this idea of chain of thought that many of you have probably heard about. So it's essentially this idea of a series of intermediate reasoning steps that improves like this complex reasoning of the model, whatever that thing is. And this paper claims that these reasoning abilities emerge naturally when the language model is sufficiently big. And you just need to give like a bunch of these chains in the prompt, and then you get like spectacular results, essentially, going beyond like models that have been fine-tuned with some kind of external verifier. Okay, so how does it look like? Well, here is the same prompt as before, and here is the variant with the added chain of thought. So we're saying, well, look, in the first task that I gave you, in the first example, the first shot, I'm giving you also the reasoning for this. So, well, we started with 5 balls, then 2 cans of 3 tennis balls yield 6 tennis balls. 5 plus 6 is 11, and so the answer is 11. And now what the model does when you include this part in the prompt is that it tries also to include the same kind of reasoning applied to the new instance of the task. And so now the model outputs, well, the cafeteria had 23 apples originally. They used 20 to make lunch, so it's 23 minus 23. And then they bought 6 more, so it's 3 plus 6, 9, and then the answer is 9. And this seems enough to get the same model to get to the correct answer for this specific instance. And so we have like this big set of thinking or reasoning language models, Now, of course, I won't go into all the details also because there is like this recent papers that tries to look at the whole taxonomy of mechanisms that people have been using. And chain of thought, the one I've just described, is up there. And so there is a very large set of techniques. But they all contribute to making like this thinking or reasoning language models. And so now that we are all on the same page with this, we can go back to our paper. So what did they do? Well, they took a bunch of tasks. Specifically, here is one task. It's the rather famous Tower of Hanoi. So there are like these 3 pegs and then a number of disks. And the goal is to move all the disks from the first to the last peg. And we have a bunch of rules that we need to satisfy. So we can't like move disks around freely. We can only move one at a time. We can't place a larger disk on top of a smaller one and stuff like that. And the interesting part about this, this task, or as the authors call it, this puzzle, is that the complexity of solving this puzzle is determined by the number of disks at the beginning. So assuming that the number of pegs is fixed here at 3, then the number of disks that you have there at the beginning determines the complexity, or better, how many moves you need to do at minimum to solve this task correctly. So there is actually this relationship that for this puzzle specifically, you need at least 2 to the power of n minus 1 moves in the optimal case. And so while they took this task, they encoded it in an appropriate format, and they gave it to the models to compare how the thinking models were doing with respect to the non-thinking counterparts. Now, for their experiment, they didn't ask the model to produce the optimal solution. Any solution would have been fine. So we have like this comparison between the thinking model, always there in quotes if you want, and the classical version, or the non-thinking counterpart. And then they have like these 3 areas, or as they call it, like 3 levels of complexity. Low complexity, that is like for n equals 1, 2, and 3. And what you see there, that for at this low complexity, essentially the 2 models perform essentially the same. They perform both very well. Maybe for n equals 3, the classical model even outperforms slightly the thinking model, which is kind of surprising in a way. Then at medium complexity, things start to behave the way we would expect it to be. So the thinking model is clearly doing better than its non-thinking counterpart. And then at a high complexity, both models fail to solve the task. And what is interesting also is that we can look at how much is the reasoning effort of these models. So we can look how many tokens are they spending, how long do they take to reach the solution. We have like at a low complexity, the thinking model is starting to use already for n equals 3 quite a large number of tokens for a relatively simple problem. Then it increases quite a bit rapidly for medium complexity. And then at a high complexity, it peaks around n equals 10, and then it drops slightly. So it seems like almost as if the model is kind of giving up on the solution, and this is beyond my capabilities. So this is quite some interesting data. And then they didn't only look at one task. You say, well, maybe it's just because of, I don't know, there is something in particular about Tower of Hanoi in the original training data set. Let's look at a bunch of maybe less, I mean, some of them are also quite well known. Maybe the last one is less known, other puzzles. So they all have this characterization where you can kind of tune the complexity of them. So we already talked about the disks for Tower of Hanoi. The second one is checkers jumping. You need to move like all the checkers from one side to the other. And so you have like these 2n checkers that you need to move. Or there is like this river crossing puzzle. I'm not going to explain the whole puzzle, but there are like some constraints. You need to place individuals on a certain boat, and there are like certain rules for who can go with whom. And so you have there the number of individuals. And then these block words, there's also some kind of block rearranging puzzle. And so the interesting thing is that now that they can place all of this together, and they can just argue about low complexity, medium complexity, or high complexity, irrespective of the specific task. And they looked again at the performance of the model. So this is performance across all tasks. Like the first one is low complexity, central one is medium, and last one is high. Horizontal axis, how many tokens do they need to reach the solution? And the vertical axis, what is the percentage of the cases in which the model produced at least one correct solution within k attempts? That's a standard metric in evaluating these benchmarks. But the main point here is that, well, the results that we got for Tower of Hanoi replicate on this mix of 4 different tasks when we account for the complexity level. So for low complexity, the non-thinking model is still doing better than the thinking one, like fewer tokens and more accurate. At medium complexity, the thinking model does better, and at high complexity, they both don't do well. And these charts have all been produced with this Claude 3.7 Sonnet, but they also looked at DeepSeek and R1 as the reasoning model and V3 as the non-reasoning counterpart. And you don't really need to look at the plots, but essentially the results replicate. So it really seems to be independent from the specific model. And now I've gave you like a lot of plots, but what I think is also interesting is to look at what's going on when these reasoning models fail on these tasks. And likely the authors in the appendixes provided a bunch of qualitative examples that I think are quite interesting. One aspect is that these reasoning models may end up overthinking. So here is a specific task. Okay, it's a Tower of Hanoi puzzle. It starts. Okay, let me understand the problem. Some tokens there, and then it quite soon gets the solution. This is the case n equals 2. So it's a rather small problem, and it already arrives, and this is already the correct solution for this task. But the reasoning model doesn't stop there. It goes on and it says, well, let me double check this solution. And then it double checks the solution, and it arrives at the conclusion that this matches our goal configuration, so our solution is correct. But it doesn't stop there. Then it says double checking, and then it goes on and on and on again to double check. But it's still not satisfied. Actually, let me review carefully the problem statement once more to make sure that I understand it correctly. And then it repeats, and it still arrives at the same correct solution. And then actually, I just noticed an ambiguity. And then it starts to double check again the problem statement and arrive again at the same solution. This is wasting like a lot of tokens. Actually, I'm second guessing myself. This is all still part of this big long answer. I just split it over several slides. And finally, I think the model says, actually, I'm overthinking this. Funny, the model itself uses overthinking. It uses one last final check, and then it's right. Okay, so in summary, the answer is moves, and it's still the same initial correct solution. So this is an interesting aspect. Now, why does this occur? I'm not entirely sure. I guess nobody really is. Still, a bunch of interesting aspects. Like this generated like a lot of debate in the community, to the point that the newly revised version of the paper has a whole appendix on response to main criticism, which I think is kind of healthy. I guess one of the points there was, well, maybe people says, well, maybe you just gave like this n equals 10 or something, and it's exponential for Tower of Hanoi. So it takes like a huge number of tokens to reach the correct solution, and you're going beyond the context limit. So you're not really noticing genuine failure of reasoning. But the response is, well, all the problems are well within the context limits in all puzzles. And what's interesting perhaps is that the first failure move happens relatively soon in the reasoning trace. And here is a plot that shows this. So when we only look at the reasoning model and we say, well, at which point in this potentially very long reasoning trace does it find the candidate solution, the one that it outputs, okay, this is my answer now. We can see that for the correct solution, that is like this hexagons part, the model can waste quite a lot of tokens before arriving at the correct solution, especially there in the middle. If you see it, it finds like the correct solution for n equals 8 at almost or above 80% of its reasoning trace, so it only arrives at the correct solution quite late. And for incorrect solution, maybe the most interesting aspect, the incorrect one that is decided by the model happens relatively early in the reasoning trace. If you look there at those crosses, it's like between 20 and 30% of the trace. So already after 10, 20, 30%, it already made an incorrect move. And then from there on, kind of the reasoning falls apart. And they again have like a qualitative example that I'm not going to go through this time. But just to show you that there is a wrong conclusion here at the end. And the first failure occurs essentially immediately. Like the model says, OK, I'm going to do this. And then it says, well, actually, I don't think I'm allowed to do this because this seems to violate one of the constraints, but it actually does not. And so this is a very or a relatively early failure, and then reasoning sort of collapses. One final aspect that I think is kind of interesting says, OK, well, but we have like these problems. These are sort of well known. Can't we just give the algorithm to the model, and then the model is going to figure it out automatically? So here's what they tried. Let's write some kind of algorithm in pseudocode, and let's just give them this in the prompt to the model, and maybe the model is going to be able to solve. I mean, these models seem to exhibit quite sophisticated understanding of pseudocode or Python, and the answer is unfortunately that giving the algorithm seems to bring almost no improvement to the model. They tried this for the Tower of Hanoi and the checker jumping tasks. They tried on both the DeepSeek and the Claude models. It doesn't seem really to help. So what is the conclusion? I'm not sure. I don't have like a big conclusion here on this illusion of thinking. I though kind of resonate with this Reddit comment that said like the reactions to this paper, the sensationalism, social media posts, confirmation biases, people discussing it without even actually reading it, let alone trying to poke holes. It all goes to show that human thinking is mostly an illusion. OK, on this sad note, thank you.